Hello, today we are going to dive into deep learning and generative AI. And our outline for this lecture is going to be as follows. We're going to start with the definition and motivation. So we will cover machine learning, deep learning, and I'm trying to provide a summary, I would say an overview. I really made it super quick. It summarizes hours of watching and learning. So I am trying to summarize things in an effective way for machine learning, for deep learning, because these are the basic foundations, I would say, and the basics so we can move further. Okay, next we are going to learn about data representation, which is mandatory to understand and map input to the different learning techniques. Okay, after that, we are going to dive into some particular type of learning, which are the generative methods, and we will take the example of Gaussian mixture models or GMMs. So we are going to take them in, I would say, abstract way. We are not going to dive into the details, but I have a message that I will try to deliver, and it will just introduce you guys to generative modeling, and then we are going to learn about the latent variable. Okay, so we remember that we were talking about different definitions related to AI, machine learning, deep learning. And for me, it's a must to understand what is AI and to answer accurately to this question. Okay, so AI is the field of computer science that aims to build, like we were talking last time, capable systems, and they are performing tasks that are normally require intelligence or human intelligence. This is from where the word in artificial intelligence, this is from where the word intelligence is coming. Okay, examples of tasks that require human, I would say, expertise or intelligence are, for example, perceiving, reasoning, learning, decision making, problem solving, and so on. Okay, so at its core, AI is about creating machines that can sense their environment, that can, I would say, interpret information and learn from experience. So they will be able, the machines, I mean, to act towards achieving some goals. Like humans, we were talking about the example of Baby Yahya last time, if you remember. So often with the ability to adapt and improve over time, which is taken from human example. Okay, now, so usually when I teach I would say a full AI course, I begin with classical foundation. I start with problem solving, which means I cover topics like how an intelligent agent can search through possible actions to reach a goal. I probably discuss some algorithms like the DFS, BFS, greedy best first search, A star, and so on. So after that, I move into adversarial search. And in this case, what I teach, we discuss about agents and how they must plan against an opponent. Okay, in this case, probably we can cover algorithms like min-max, like alpha beta, pruning, or even depth limited min-max. Okay, why I'm telling you all this? I'm telling you all this as an advice from my side. If you are one day going to take an AI class, don't be afraid while seeing all these terms or these algorithm names. They are not scary at all. I remember I was sharing the syllabus before the first week, and now I don't share my syllabus early. And I had lots of students in the AI class, and after that I shared that detailed syllabus. So the students thought that this is very complicated. What is this? So I don't want to think like that, because these are things that you must know. They are the foundation of AI. Okay, so after that, what I teach after all these algorithms, I probably move to knowledge representation, how to represent knowledge and uncertainty, like how to model uncertainty. Okay, how machines can represent facts, for example, reason with logic, or how can machines like handle uncertainty using tools such as Bayesian networks, or even like Bayesian nets over time for the dynamic situations. Okay, so all this I usually covered in kind of like typical AI class, or I would say this is a traditional picture of AI, and it's important to see where modern method from where the modern methods that we are discussing in this course are like coming from. So historically speaking, AI started with rules and symbolic reasoning. So started from that. Essentially, we used to have the pen and paper, and we used like logic. And so with the rise of computers, we could automate more complex like search and planning things. Okay, then as data and storage grow, we shifted into machine learning. Then machine learning is coming with more computational power. It's coming with more advanced like resources that we are having, and then with the still we are like having more technological revolution, I would say. So this took us into deep learning, reinforcement learning, and now generative AI. Okay, so this class is not mainly designed to cover all AI or AI. We are focusing mainly on generative AI. Okay, but I am trying to connect like things. I'm trying to approach the border, I would say, of AI landscape. So in this case, I believe that it will help you understand how the field has evolved from like these typical, like for example, search and so on, examples, until what we see today. Okay, so this is mainly the idea. So the powerful generative AI tools or models that we have today are mainly coming like from the basics or the foundation that we had, I would say, before. Okay, so I would love to start today's class about this motivation from where we started. So the idea of AI, and here I will focus on the subsection of AI machine learning, it came like I would say in 1950, Alan Turing, and if you might heard about the Turing test, like the competition between the computer and the human, and then the computer is, I would say, winning and so on. So this is introduced by Mr. Alan Turing, okay? And it started with this sentence. It started with this sentence that has been published in one of his papers. So he mentioned that I propose to consider the question, can machines think? It's very like deep question. Can machines think? Okay, so this simulates things. We started from here. And so we are like, if we think about can machines think, so means kind of, if we translate it in other words, can machine think like who thinks in this world? Like humans? And let's say if we only do not consider humans, can machine like do some like tasks that other creations does? Like for example, if I have a machine which is in this case a plane, so mainly a plane as a model is designed to do something that a bird does, but we will come back to this. But the car here, this car is designed mainly to be fast and to run fast, I would say, like this animal has been created for. So with this, but now I'll come back to the question or the contradiction. But is this car really like the animal? Is this plane really like this animal, like this like bird? So in this case, it's not, but it's a model implementing some features that naturally exist in some like beings. Okay, so this is the idea, but how we did that? It's like long journey. And this journey, if you remember, started from learning, okay? Last time we saw that baby Yahya, for example, he learns like in two ways mainly. We see that he learns whether like from parent-child or teacher-student relationship, okay? And that was supervised learning. In this case, kind of knowledge and like labels given by someone who already knows. So we are people who know the word, and we are teaching him how the word works, like I told you last time. So the second like type of learning we seen was reinforcement learning. Okay, so this is the way that baby Yahya learns through goals, through feedback, by trial and error, by seeing what works and what doesn't work. So this was reinforcement learning. Okay, so now baby Yahya, he can also learn in other ways. Okay, for example, sometimes he just explores. He opens like drawers or group his toys or notice that some food tastes similar. So no one told him these like the categories. He discovers the structure by himself. Okay, this is exactly unsupervised learning, means having the data but there is no level, and he's just trying just to find kind of hidden patterns or clusters. Okay, this food is tasty, this food is not tasty, for example. Okay, so there is also next probably you can imagine another situation where Yahya is holding a book. For example, here we have cat and dog, but nothing, or let's say no explanations what the book is. You see, so by his own, he's just like maybe connecting dots, or like he figures out the missing category on his own. So that's kind of semi-supervised learning, which is, I would say, a mix of few labels. Then, for example, these few labels are there to guide or to help, and mostly it's self-discovery. Okay, so if I try to put like all this, we can have supervised learning, which means we have training data plus desired outputs or labels. Unsupervised learning, we have the training data without any desired outputs. We can also have the semi-supervised learning, which means that we have trained data plus few desired outputs. And lastly, we can have the reinforcement learning, which means that rewards from actions and feedback. This is how it works in summary. So these four approaches give us the main foundation of like how machines can like probably I would say machines, or here I'm taking the example of baby Yahya, but now we talk on machines, how machines learn, or is inspired by how probably humans are learning, or the learning process itself, or our own understanding of learning as humans. So how machines learn from the world. Okay, these are mainly the four types. Okay, next, now we can go through some machine learning, like first of all, the definition. So machine learning is a field of AI that consists in programming machines so that it learns to perform tasks. Okay, so the machine is going to learn to do something, which is the task. And how? It's by studying examples representing these tasks. Okay, so when I say examples, these examples, what are the examples in the case of a machine? Can pause the video and think of it. So examples are data when it comes to the machine, okay? And data is like, for example, these data points, okay? We have, in this case, an example of a model, okay? So we are thinking how the machine is going probably to solve this problem. This is known as regression problem, okay? And our data in this point are in this case are the red points. So what our model is going to do, we have in this case a simple linear model, which is just a line. So this line is, let's say, following the trend of these like points. It's showing kind of a representation, which is a model that all these points somehow they are following. Or so it just, I'm trying to make things simple. So this is the model, and if we talk mathematically speak, so it's like a function f of x, which is like, it's known as the linear function ax plus b. So suppose that b0 starts from here, otherwise it's a field case, but let's keep it simple. Now, I was mentioning that this like line, it's mainly, I would say, learning from this data. It is like representing probably this regression problem. So we could have many lines. So we would imagine this green line starting somewhere else. I can have it positioned here or here or here. So how to do, or how to finalize, I would say, or have the optimal model, okay? So it comes up to what we call optimization problem. So I have infinity of possible like lines. And when I say infinity, it comes from the fact that these A and B are my parameters. So they are like, could have different values. And the X, so each time it's vary as a function of X, okay? So each time we vary these parameters, we can get different like position of that line. And what we want, the optimal or the best thing, is that this like line is mainly near or the nearest to most of these points, okay? This is how it's learning, that it's minimizing the distance to these points, okay? So this is a representation of the line and the final model, how it's like learning towards the optimal like representation. But in the, I would say, hidden side, the idea is about minimizing some distance. So we are starting from something which is random, and we are having some errors. So this is not true that the line is this much far, like in this case. No. So we each time to compute the distance, for example, or we have measurements for this. So we try to check each time, compute the error. There are different types. So just here we are having the mean square error. And while computing, what we want to do, moving with the steps. So whenever I am near from the points, I try to move slowly. If I am far, it's okay to jump. So here we are just reducing the size of the steps until falling in that minimum and like, I would say, perfect, somehow, for sure. I would say good fit, let's say, good like position of that line. And then we say, okay, here the model is trained and everything is okay. My machine is learning. Okay, so we are discussing about machine learning. The idea mainly, so it's to develop a model using an optimization algorithm to minimize the error between the model and our data. So this is machine learning, okay? Now, when we talk about machine learning, there are three main categories. There are what we call generative methods, and generative methods like mainly we have they model the data distribution, okay? And we see probably the example of k-means. Today we will see the JMM, but let's see how k-means works, okay? So mainly k-means, it's clustering algorithm, and it like creates clusters, or it clusters the data by iteratively like assigning points, okay, to the nearest centroid, and it keep updating the position of these centroids until like it converges, okay? So at the end, we start with random, and then, for example, we find our like final, I would say, clusters. So they look like this, let's say, okay? So this is for generative methods, in particular K-means. Next, so we have the discriminative methods, and discriminative methods mainly, they directly learn decision boundaries, which means that the model here is going to like give you the decision boundaries. We have the example of KNN, which stands for the K nearest neighbor, and the idea behind KNNs is kind of classifiers, and it classifies it classifies the data point so based on its neighborhood, which means it's kind of a vote. Given the majority labels of the K closest neighborhood in the feature space, we will decide if a given sample is, for example, belonging to this or to the other class. So it's probably more near to the green, I would say, class. So we can put it with the class B, okay? And next, so there is what we call the ensemble methods. And ensemble methods, they combine multiple methods. So we have, for example, random forest. And random forest, mainly it's about building multiple decision like trees. So in this case, probably we have 3, probably we can have n decision like trees. And this is based on random subsets of training data and features. And it's going to predict and then also aggregate the output from each of these like models. So it's, for example, the majority voting classification, okay? We mainly decide based on the majority or like average for regression, okay? So these are our 3 classes, but so when we talk about machine learning, at some given point, we had big data. We had a hardware revolution, which like, for example, we have better like GPUs and so on. Also software has been like improved. We have new models and so on. So all this together made things ready and started to prepare for something new, or I would say revolution, which was deep learning, okay? We're done for machine learning very quickly. Now we are moving to deep learning. It will be also quick, don't worry. So deep learning, I'm trying to summarize things. What is deep learning? Okay, typical answer. It's a subset or subfield of machine learning, which itself a subfield of AI, okay? But the idea of deep learning mainly is that it imitates the way that humans gain certain types of knowledge, which means like humans in there, if we focus in our design, how we think or what is how it works. So we will focus on our neurons, and this is an example of a biological neuron you can see over here. So a biological neuron usually has dendrites. So these are mainly the neuron from where the neuron receives its inputs along like it's kind of internet-like structure, okay? And it means like if, for example, I'm putting my hand on something which is very hot, okay? Let's imagine. And I'm touching something very hot. So it's like I'm receiving some input, okay? So until here, just I'm receiving. Next, what we have in these neurons, the cell body. So the cell body is after being weighted by strength and their respective connections, the inputs like are summed together in a cell body, which means if I'm putting my hand on something which is very hot, I'm touching, it's, I would say, abnormal. I'm just receiving with the dendrites, and then the cell body is analyzing. There is something. So there is a function. There is something. So strength, if in case it's extremely hot, okay, and then it's going to be, I would say, propagated through the axon, which is going to transform it into a new signal, and this signal is probably going to go along the cell axons and send probably to other neurons. Okay, so this is a signal. It's extremely high if that what I was touching is very hot. If it's normal, not that hot. So this like signal is going to be not that high. Okay, it will reduce. There will be no reaction. If I'm touching something extremely hot, then I can just take a decision and take my hand. So it's like this. So this is how a human or biological neuron works. Okay. Now we started from here. We started from the idea of biological neuron. And what happened is that in 1943, the idea is coming of the first artificial neuron. So it's all about modeling. So we created the model of this biological neuron, and this model is to represent it as simple as here we have some function, okay, for my cell body. I have some inputs for this function. They're exactly like the inputs coming through the dendrites. These inputs, as I was mentioning, I can hold something which is extremely hot, something which is extremely cold. So in this case, it's extreme. Something that is moderated, I would say, and I can touch something which is okay. So moderated, okay, extremely hot or cold. These are weights. It's giving the importance of these inputs that I'm touching. So as simple as this representation, given the X inputs, the importance of these inputs notes by Y's, W's, which are the weights. I have a function. This is the model, okay? The function is going to compute some output, okay? This output is denoted by y, okay? And what we have is a threshold logic unit, which means that the aggregation function f is a function of, we call it the sum of products, which means we are going to have the importance of x1, which is w1, multiplied by x1, plus the importance of x2, which is the weight of for x2, w2 multiplied by x2, plus the weight or the importance of x3 multiplied by x3. So this is just the aggregation function f. Now the decision is going to be based on the result found in f. If this is like positive, I would say, greater or equal to 0, then y is equal to 1. So it's binary. It's 1 or 0, which means it's activated or it's not activated. So this is the first artificial neuron in few minutes. From that, so this is just a simple one, just a model, and it has y 0 or 1, nothing more than this. But we're introducing something very important, which is the threshold, okay, logic unit. It's very important. Even that is binary here, but it's very important. Okay, so now the idea is that it's not like whenever I have sum of products and I just have the final output. No, there is something we call learning algorithm, which means that these outputs, they keep like impacting the input. It's like a learning. I will learn from the Y. If like someone is learning from his mistakes. So this Y somehow it influences the X, and how when I say it's influence the X is the input, it does not change. So the way it influences the X actually is how it like it influences the importance of that X, which is the weights given to that X. Okay, so what we can change in this function are mainly the weights, and what we add the bytes here, it's just like scalar. Okay, so this is what we learn, is that there is a learning, I would say, process or algorithm, and which makes that move from the threshold logic unit to like output that looks like this, like y is equal to 0, for example. Whenever it's negative, it's equal to 1. Whenever it's like positive, and so this like could be translated into like understanding the way that it's mainly a start of understanding how the neuron of our brain in the artificial, like I would say, model works. And this was really useful, okay? So this was mainly useful to solve some problem, and they are simple problems, like they are problems that you can separate just with a line. Means I would say just like in the classification problem, if I have like this data points, and the red one represent class 1 and the blue one represent class 2. This kind of models is like helps, or it's able to like get this decision boundary, okay, because it's simple. But like it's not like a linear model all the time. So perceptron is perceptron is a linear model, and the problems that we often like or usually most of the time face are like non-linear. So we could sometimes face more complex situation, more complicated situations. Like here, it's very difficult to find the line that exactly separates. So each time you will find some red with the blue, some blue with the red. So this problem is called non-linear. So if I want to solve this problem, probably the best fit for this, if I will say, it can be something like this, that like the surface or the boundaries for the decision, they are not non-linear, okay? Linear when they are like this line. Non-linear is when you are somehow having some, I would say, like curvature moving, and it's like a circle somehow. So it's not a straight line, okay? Maybe at some point when we focus on, like, for example, I will take only this part, okay? And I will just zoom on it, okay? If I will zoom, it's, each time there is a little linear function, okay? Keep this in mind because it's very important. A non-linear function is somehow combination of multiple linear functions, okay? But forget about this for now. Let me delete this so we don't keep following us until the end of the presentation. So what happens now? What happens is that we need to solve, as I was mentioning, more complex nonlinear problems. And in this case, like Maclush and Pitts, what they say that by connecting several neurons like this one together, so we try to connect many neurons together, it's possible to solve more complex problems than when we are having only a single one, okay? So from here, the idea of artificial neural networks, okay? And the idea of multi-layer perceptron, okay? So multi-layer perceptrons is like we have one input, this is your input, so it's called one input layer. You have one output layer and one hidden layer. So this is a case of MLP. Artificial neural networks when you have couple of layers in between, but few layers, I would say. But sometimes this model can have a lot of hidden layers, and this is what we have today, billions or millions or millions and billions, sorry, of parameters. So in this case, it's called deep learning, okay? This is basic architecture. How it works, and I never thought that it will come the day that I will make deep learning in 5 minutes or quickly means I will explain it. So it's happening. So what we say or what we have in here is the algorithm, how it works briefly. So in the start, we have our input layer, all these our hidden layer, and this is our output layer. Remember that input, it's given to the network, and this, let's say, the network. The output is the label, okay, because we're giving an input, example, image of a dog or a cat, and we know that this is a dog and this is a cat. What this network is going to do is it's going to guess. It can guess the real or true label. It can make some errors. So in this case, we talk about the error calculation, and we need to optimize this error. So we keep like going, having what we call a forward pass, also forward propagation is the same word. So forward propagation means for the input we're going to go from input through all the hidden layers in order to the output, okay? Compute the cost function, okay, or the error, and then what will happen is that we'll try to update the connections, the importance, the weights. So in order to like converge towards learning. So this update process is a backpropagation, okay? And each time we keep like using the gradient descent, okay? And so mainly this is how it works very quickly. Now we have an overview about deep learning. We have later different architecture, some for vision, like we have image classification, we have the powerful convolutional neural networks, which are particular architectures that I was detailing and providing you with materials to cover that. So there are recurrent neural networks. There are many types of neural networks, many architectures. And so this is the idea of neural networks. Now, neural networks are not only designed for images, we have them for multiple data types, multiple input data types, okay? So this is why I'm going to briefly go through data representation, because it's different how we see the world and how a machine sees the world, okay? How a neural network, for example, sees the input is not the same like how I, as a human, will see that input. Taking this example, this is an image, and taking this from LinkedIn, so I'll keep the link for you. So what I see here is this eye, part of the eye. And this part of the eye, really, it's like a grayscale image, I would say. It's having different level of grayscale. So if we can translate it with numbers, and we can focus with every particular part of this, part of the image. So we have it composed of many what we call pixels, okay? This it's a pixel, and this is a pixel, and next we have another pixel. It's like that. So every pixel has a color, okay? And every color is having its code. And so here we have the values, for example, between 0 and 128, or 0 to 155. It depends, okay? This is mainly how computers see, okay? So they see these numbers, and I'm that much making machine learning so simple and deep learning simple and life easy. It is easy, but they always say that there is a lot of math behind. Math is really here. When you think about this, like how the computer sees the image, you see it in this representation. This is actually known as a matrix, okay? So this is a 2D matrix. So this is a 2D representation of the 2D images. So we have here across the first dimension, we have here is across the second dimension, okay? And so here we are reading in this 2D space, the mapping for each pixel, what is the exact value, okay? So this is just the grayscale image, but we have another category of images, which are the color images. So for color images, probably we are going to consider that from where colors come, so mainly from a combination of three basic colors, which are red and green and blue. The RGB space we called, okay? So for this RGB space, what does it mean? That the computer is going to see three channels encoding or representing your image. And for each of these channels, there are numbers for each column and each row. So you can read it like this. There is a position. And so how it reads like this, okay? This is for the first pixel. For each pixel means you are having in these three matrices, you have the three values. So this is known as tensor representation of an image. So it can be multi-dimensional array like this one, okay? You have, for this is one, the dimension 1, dimension 2, dimension 3. And here, for example, you have the three channels, and as I mentioned, they correspond to the red, green, and blue color intensities, okay? So this is mainly for color image representation computer vision. But also deep learning or machine learning, mainly deep learning, I will focus now because we're moving toward generative AI. So they are also very powerful when it comes to natural language processing. Like, it's not always the computer sees an image or a face or a human or a cat or a dog or whatever. It could see some like text, okay? Words, okay? In different languages. So here, for example, I have the word apple. How the computer is going to see this word apple or understand that? It's what we call the vector embedding. So this is a matrix, okay? Writing and this is very difficult. Ooh, what are I writing? So this is a matrix, and this is a tensor, okay? Like you hear about TensorFlow, right? You will see tensor, and this is a vector. So what is the difference between the matrix and this vector? So here we mainly have it in one dimension, okay? So vector embeddings mainly are dense numerical representations of data that capture the semantic meaning of the text. Can also capture, if we can see this like many for images, for example, for audio, for other types. So they transform complex and unstructured data into some structured numerical format, okay? So I'm making it very simple. Otherwise, believe me, each of my slides probably you need to have a class behind that. So for 1 to 2 semesters, but I'm giving you the basics and the overall picture. Okay, this is what I care about. If you have any questions about any further details, I'm always available, and you can ask me. It will be a pleasure for me to like discuss. So we need to clean this first. So whenever we are moving to the next slides, this is not going to bother. Okay. Sure, there is a more like quick way to do it, but it's fine. Okay. Yep. We were discussing about machine learning. Then we seen that we went through the evolution and all that. We went through deep learning. Now from deep learning, we are supposed to go to what we call generative, like AI. This probably can take us a step back when we're talking about machine learning, and there is something called generative methods. So probably it's very important to use that as a bridge. And we are going to see the GMMs today, which are the Gaussian mixture model, okay? For that, so probably we need to start with the Gaussian density estimation, which is very important. So whatever I'm covering today, there is a lot of maths behind. I love honesty, and I love to be honest with you, but I'm making it in that abstraction that everyone will understand, because I know this course is designed even for students or people who do not have any background in AI. So I want to make AI, generative AI, accessible. And so let's discuss about Gaussian density estimation now. So it's kind of a model, or it's, I would say, soft probabilistic clustering model that allows us to describe membership of points to a set of clusters, okay? And in this case, what we will use probably the mixture of Gaussian densities. So it's a soft classification method, which means like, I will give this example. I have a set of data points, okay? These points, I don't know, like if they belong to which class, okay? So probably I can have 3 classes, okay? And these data points belong to these, each of them belong to one class, okay? When I say belong, here belonging is not binary, which means it's not hard, clustering, it's soft clustering. The difference is that when we talk about hard clustering, it's binary, means it belongs to the orange class with the 100% probability 1, or it doesn't belong to the orange class with 0, there is probability value 0%, and it is belong to this class. So whether you will find yourself in here 100% or here is like 0, okay? Belonging. This is for the hard, like, I would say clustering models. For these, if you see, there is like a shape. It's the shape of the bell. It's a bell shape, okay? So for this bell shape, it means like here, this, whatever, for example, here in these like regions is belong with a very like a low value, probability value to the orange class. The more we are like going through the like towards this point, the maximum means that the more this probability value increases, okay? So here probably this point belongs like, let's say 80%. This point probably belongs with probability 30%. So we are becoming more flexible, and it's not like yes or no, it belongs or does not belong. It belongs with some probability. Let's take the example of this like point. So this point belongs with a respectful like value here, percentage. Like let's say maybe 35% to the blue because it's almost near from the peak. But the same point belongs maybe 1 to 2% to the orange because here it's the value for the orange Gaussian. It's very less, okay? So this is like we try to assign like samples based on probabilities of belonging like to a specific class instead of like definitive choice, binary choice, okay? Like in this life, it's not even binary. It's like not dark or white, okay? There is in between. There is the like morning time, sunset, and so on. There is not like black and white or day and night or all these contradictions. We live in a world where it could be like cold with some percentage, which means that it's hot with some other percentage. It's not cold, strictly cold or strictly hot. Okay, so keep the slide. And now what we have? We have these observations, and we have that they're belonging to every class, probably percentages, and we have different probabilities. So we are going to consider the famous examples. So here probably how many classes you have? You see 3 Gaussians, so probably there are 3 classes. This is why we'll take the example of iris flowers. It's a data set of 150 images of flowers, and we have 3 I would say main classes. But given some features, like for example, the sepal length and width, and the petal length and width. So we can identify the class, okay? So these are our 3 categories, I would say. And you see these data points now, we can like assign them to the classes from where the colors are coming. So these belong to the Setosa category, for example. This is to the 2nd category, and this is to the 3rd category. Okay, so this is the idea of Gaussian mixture model, which is based on Gaussian density estimation. And so I took these screenshots. Actually, I keep links like all the time whenever I take notes from some source. So for those who love to go beyond the class lectures, probably if you have some math like basics you want to explore, you can go through the Gaussian mixture model. You can go even further to the expectation maximization algorithm and all this. So I'll be really happy. In case you don't, so it's not the main target from this class. The main target now for me is to understand the Gaussian density estimation with this example of Gaussian mixture model, which from here unlabeled data. Okay, we don't know at this point the label. These are new samples coming, new pictures of these flowers. Probably we can identify their belonging if they belong to which category. So this is mainly the idea. How it works now? Well, in fact, so solving this is not that hard. We just have to start somewhere. Okay, let's suppose we're starting here. 1, 2, 3, super good. we start here, we end up here. Okay. So we start somewhere which is random. So we can set some Gaussian parameters to random values. So we will have random position of our Gaussians, and then we perform some optimization by iterating through 2 successive steps until convergence. First one, that we assign labels to the observations using the current Gaussian parameters. And the second step is that we keep updating the Gaussian parameters so that the fit, like it's more likely this will give the following results, like this final point. So in gray here you have your final probably how it can look like, and then these like green, like purple and blue, they show how like the model through the different steps is like updated and ending up by converging. Okay, so mainly this is like our case. We have 3 classes, 3 types of flowers, and we have the data distribution. We can also fall into some binary class, which means that we have only 2 classes, this one or this one, and we will consider belonging with percentages to each of these classes, these probabilities. Okay, now I am going to move quickly towards the generative modeling, which everyone is waiting for. So our goal in this case is that we take an input training sample from some distribution, and we will learn like a model that represents this distribution. Okay, so this is mainly based on the density estimation. Okay, and we are going to be based how the probability distribution is like going to look like. So our goal in this case is to train the model that can learn this distribution. Okay, the one that can describe or describes and captures, I would say, the space from which the data came. Okay, so this is our data, and somehow we are capturing the model that presents that data and from where, okay, this data came. So once we learn it, the model can somehow sample from the probability distribution to generate brand new instances. Okay, and so this works because the model has captured the underlying structure of the data. It learns patterns, meaning like the generated samples, they reflect the sample distribution. Okay, I would give you the example here. If we have our input like samples, we have these images. So it's maybe this is our training data, it's input to the model, and it has some probability values or distribution of this data for each X like data point, I would say, or image. From this, probably we can generate some samples. Okay, and these samples, how are they generated? Mainly, they are generated thanks to the generative modeling. And the key question in this case, like, is how we can effectively estimate this, like probability P of X, probability density, or probability distribution, so that it is as close as possible to the true distribution. Because mainly I want the generated images look like quite similar to the input images. Okay, I don't want them to be different. So I want this similarity. That is the core principle of generative modeling. It means learning a probability distribution that represents your data. Okay? Okay. Yep. So now the question is, we are having why generative models? Or we need to answer some concerns. I would say few questions or reasons why generative AI is useful. Okay, I'll give you 3 reasons. Probably the first one is de-biasing. When we talk about de-biasing, it's coming from the word bias. And excuse me, what does bias mean? It means like sometimes when you have a model and you are giving the model like this type of data, For your model in this case is known as trained on base data. So the result is not like something that would work perfectly if there is huge changes in the images. So probably it only works your model well. It can give you 100% accuracy. Why not? In case only when you have some homogeneous skin color or pose. So maybe it's trained on the same thing, which is not the real case of the real world, because mainly we have different faces, different skin tones, and we could have pictures of people, or I mean faces in different poses, in different light conditions like illuminations, contrast, and so on. So if the model now is going to be trained given this like I would say more rich data set, so probably it will generalize better, which means if there is a new input, it's already in multiple like positions, multiple examples, and it can work really well. So creating probably this type of data set can be done, or generative AI could be helpful for creating this type of data sets. So it can be useful for generating data. And so we can use this information probably to, I would say, try to create some fair and representative data sets, okay? But it's not like guarantee, so we are trying. This is what I can say, okay? Because fairness is very important. At the end of this class, probably we'll go through some like topics related to the ethics and the base in AI, especially in this, I would say, crazy time. And so the second reason is that, for example, the problem is how can we detect when we encounter something new or rare? So I always give this example: rare cases or new cases are known as outliers. Outliers are some things like, I would say, different, like of the group. You know that story of the ducks. There is they are all like I think one black, it's something like this. And so outlier is someone who is not looking like the, I would say, the group, okay? So the group in this case is something which is usual, something that we face all the time. The pictures that repeat, for example. So in the context of, I would say, autonomous driving, we have the car, and usually the car, how it works, it's getting the input from the outside world. So how it's taking this, like in the many images captured each, I would say, second. Based on that, probably you are taking the decision. So most of the pictures, or I would say 95% of driving data, whether it's a sunny highway or a straight road. However, there are some cases, so 95% means we are almost here in the, like, if we respect this Gaussian distribution, which is the majority. So majority of the data, it's here. However, there are some few rare cases, okay, that we can detect outliers in this case. Outliers, like, for example, there is a plane, or there is some rainy day, or someone is there blocking the road. So these are outliers, and using generative models, we can like detect these outliers, okay? It's one of the reasons. So I would probably give you a last reason. It's for generating samples, which means like generative models learn probably the probability distribution sampling from the distribution of new data. And so this is it. So and this is mainly the basic and the very important point in generative AI, to generate whether language, we see the example of ChatGPT, generating paragraphs, generating text, and so on. We have image, the case or the example of art generation. And here it can really generate amazing pieces of art in terms of images, I mean. And also it could be like generating some medical data, like for example, in the case of molecular design, or so it's very important. This case, like for art, we don't spend hours like doing that art, it can be generated. Text, we don't spend hours doing that essay, it can be generated. In this case of molecular design, probably we do not spend that because it's very costly, okay? We don't spend that much money to discover like new molecules, and we can do that with generative AI. Okay, so this just highlights the use cases probably and the importance. Now I will focus on two foundational classes on generative models. The latent the autoencoders and variational autoencoders, okay? And other key architecture is known as the generative adversarial networks, or you probably hear about the GANs, okay? Both of these belong to broader category of latent variable models, okay? And to dive into this, the very first thing that we need to clarify is what exactly is a latent variable, okay? This is what we are going to learn. So what is a latent variable? And I don't know whatever. So here we have the shadow. So the shadow of a rabbit and probably different animals. We have here a dino, or we can have probably different shapes, like, for example, what's next? An elephant, and so on. So this I want you to learn, okay? Because it's really quite interesting. So this is like what today's babies love. And so this is going to help us to learn about latent variable. Latent variable, we are going to learn like while imagining, like we are looking at a shadow on the wall. If we have this hand probably and this shadow, it's not the hand. So what we see directly is the shadow. We don't see the hand, okay? So it's like the observed data in machine learning. So this is the input for the model. This is the observed data in machine learning. It could be the pixel in an image. It could be the words in a sentence, or it could be probably the notes in music, okay? So, but the thing is that behind this shadow, there is something else, okay? There is probably this hand, okay? It can be not even a hand only, okay? So there is something else, or maybe it's the hand probably arranged in some way, so it gives you these different representations, or this is the latent variable, okay? Cannot only be hands, it can be something else, which is like, even we have the arrangement of some objects, they arrange it in, I would say, certain way, and in this certain way, you know, it's the shadow art of, like, for example, we can see clearly it's Michael Jackson, okay? This is a man, or this is like a piece of art, someone is dancing, okay? I love it. So even now, some objects, they are arranged in some way. What we see is the latent variable. So what we understood from that, we think the hidden things that we don't see are like arranged, okay? So these hidden objects, mainly, whether here you have the hand, or you have like these different objects, like the way they are arranged or organized, they probably like show you how that like illustrate how like what is exactly a latent variable, I would say, okay? We don't see them directly, latent variables, but they just explain the shadow looks, how it looks like, okay? This is just an example, okay? I probably can give you another example. If like placing the hands in the position, I will take this diamond, for example, and placing the hand in this position, or in the case of, for example, Michael Jackson, placing the different object, having the shadow that we have, if we change the objects or the hand in a different way, like these things can change, okay? So these variables, they vary depending on how we are going to change the hands, or we are going to change the different objects, okay? So these are the things that we directly observe, okay? So in generative AI now, latent variable play exactly this role, okay? They are like the hidden representation, okay? They capture important features of the data. When the model learns these hidden factors, it can generate new outputs. So just like creating new shadow shapes, for example, we are learning probably to generate new representation. So the shadow observed, the shadow is what we observe, is the observed data. The hidden, I would say, hand or object is called the latent variable. And we have something else, a very important feature, which is the light, okay? So in this case, the light could be the generative model itself, okay? Because actually it is illustrating, I would say, the source, or it is generative process, okay? This is why latent variables are so powerful. So they let us explain and generate the visible word from hidden structures, okay? So I want you to keep these examples in mind, okay? That's it. I try to summarize because sometimes I feel I can give you the idea and the way I think, and I think I'm making it simple. I'm doing my best to give you my own examples, but I keep for you some notes always so you understand the logic, and just as a note for you, okay? So the shadow in the wall is the observed variable. And so what we actually see, like we see an animal, we see Michael Jackson silhouette or whatever. The arrangement of the objects is or the hands is the latent variable, the hidden structure creating the shadow. The light source is generated process mapping from latent variables to observed data. And different latent configurations, we have hands position, we have stacked objects, arranged furniture. All these yields like different observed shadows, okay? So we can always see or guess the objects directly from the shadow, just like we can't directly observe latent variables. And the problem is if we want to learn the mapping, so we can generate like new shadow or ever hidden objects behind a shadow. So I'm trying to summarize whatever I said so you don't feel lost at some point. Okay. This was like I was preparing the film and the film is burned. No, I will not repeat the recording of 1 hour because I'm not inserting the order. I want this to actually appear with the animation, but it's not very good. Okay, so don't consider these two. Okay, we will focus on with the first example. So what I was planning is I want to illustrate, or I want to make you understand some example to illustrate what we will see later, okay, after this latent variable, where it's going to take us, okay? So what I was doing is, you remember Baby Yahya? So imagine that I was giving, it was kind of funny prompt. I was giving his picture today, and he just now 3 months maybe. And I was saying to the generative AI, generate the picture of baby Yahya when he will be 80 years old. So what you see here is it's not a real picture. It's not a picture of someone who already exists or something. It's a generative image in a given space of baby Yahya, I would say. Okay. So actually, this kind of examples can make me personally stop for a moment, and maybe I think about many things. Maybe I think about life, memories, about the future, of course. So how powerful generative models can be. even I would say from a okay, I'm that much thinking, I cannot even pronounce the words. From a philosophical point of view, it's really the heart of philosophy, I feel. So this, like the first picture, I think it's my son. It's when he will be 8 years old. What I'm saying, it's an example, but if we think of it in terms of a human feeling, so we think that this image, okay, it's never existing in the reality. It's a generated image. There is a model that created it by exploring possibilities in the latent space. Okay, this we understand. It's part of our generative AI class. But I was thinking, when I see this picture, I said probably I won't be alive to see my son when he will be 80 years old. It's the same, like my grandmother who passed away years ago. May she rest in peace, I wish. So probably never imagined how my father would look like in his 90s, for example. She would not be here to see it for sure. So we humans are used to, probably we are using to see things on Facebook or whatever, that adds how you will look like in 10 years, how you will look like in 20 years. So it was personal. But now we can imagine like our children, our grandchildren, like decades from now in the future. This is really like something to think about. Okay. So generative AI is making big changes. Probably there is another trend you may have seen when like people like are giving generative AI their own pictures when they were like babies or child, and their current pictures as adults. And the generative AI is holding like is showing one adult holding one like little kid, and that is maybe your very first version holding your current version holding a very first version. So I don't only see the pictures, so I had the chance to read very nice posts about this and about these images, captions, I would say description. So it's people talking about their journey, their transformations. So this is really incredible how AI making humans think, okay? So at some point also, I can give you the example now of this image. Imagine now we will live in the future of the future of the past. The time is getting confused. So at some point, this picture from the future, but I wanted to show you the use case of latent variable. So I remember not far, people were sharing on Facebook kind of posts like they say, this is a picture of my grandfather or their beloved ones or whoever who passed away, and please, is someone expert to make it look like a new picture, not destroyed, not damaged, like clean, I would say, version of this. Okay. So, and then we open the comments, and so we see something like this, we see the final representation. So, which is kind of the restored version or colored version. So it feels alive again. So, doesn't it? It really feels alive. And the thing is that 3 images, they are not real. I felt dead, I felt alive, and it's AI generated. So it's, I don't know, speechless. Okay, so for the person now who posted the original image, now from this image to this image, there is a big change, sorry. So the person who shared the image, I usually see them happy after sharing, thanking the other person, which is really generative AI, though. So thanking whoever posted like the new version, and seeing this like amelioration in terms of resolution, in like it often gives joy, it gives real happiness. So this is exactly what autoencoders do. Okay, they encode complex information into hidden representation and then decode it back, restoring something meaningful, like sometimes even better than before. So encoder, decoder, okay? And This is the exciting part, probably. The autoencoders, they are just the beginning. Next, deeper, I would say, into variational autoencoders. And variational autoencoders are the models, I would say, that don't just reconstruct, they actually learn, like they go beyond constructions, okay? So they learn the whole distribution of possibilities, which means that the hidden latent space, they learn its whole distribution of probabilities given the hidden latent space. So, okay, so that means we can sample new variations, new faces, new styles, new realities that never exist. Okay, so today this is it's the idea is simple. Behind every picture, whenever created, destroyed, or restored, there is like a hidden space of information, okay? And learning how to use AI, how to use that space is what makes the generative AI so powerful. Thank you.